Hello everyone, this is our recorded discussion for Introduction to Educational Statistic. We're supposed to have this before measurement of or measures of central tendency, but anyway, it's still a prerequisite before we will have different terms we use in assessment and learning, especially in educational statistic. So let's have basic definition of terms. I decided not to include any learning outcomes because this is just for a review discussion. And anyway, let's start with the word statistic. So the word statistic is actually a science of conducting studies to collect, organize, summarize, analyze, and draw conclusions from data. So basically, the word assessment and learning, the discipline assessment and learning, is just a partner of it in classroom assessment. And when we coined it with educational assessment, basically, or educational statistic, basically, we're talking about analyzing data that we have from classroom assessment or any data that is connected with education in general. We also have what we call variable. So variable is a characteristic or an attribute that can assume different values. For example, grades or academic performance or learning interests. These are variables that govern our classroom assessment. Another term that we have to be aware of, or we have to be reviewed, okay, is data. So data, when you put value to the variable, there comes data. Next is we have population. So population consists of all subjects. In assessment of learning, mainly our subjects are learners, our learners. And when we say sample, it should be from the population. So it's a group of subjects, or it's a group of, for example, in a case of, let's say we have a population that is junior high school learners. So that would mean that our sample should be coming from grade 7, 8, 9, or 10. Okay, so aside from these basic terms that we have to be aware of, we also have to differentiate descriptive and inferential statistic. So when we are just describing data, we call it descriptive statistic. So when we collect, organize, summarize, and present that data, that is descriptive statistic. On the other hand, when we say inferential, this is generalizing from the sample that we have to apply into a general population. So it also involves estimating, doing hypothesis testing, determining if there's a relationship among variables, and of course, making prediction. In classroom assessment, one example would be if we gather all the grades from the different learning areas, and when we put that into the school form 9 or the report card, then that is just descriptive. But when we make inferences, when we decide if that student will be in the honor list, or that student will be promoted, or that student will be retained, then we're making inferential. So I hope that that is somehow a good example of how to differentiate descriptive statistic and inferential in classroom assessment. Okay, now we proceed to examples. So let's try to determine with these given examples I have here, let's try to determine whether we can say it's descriptive or inferential. So you can go ahead and pause the video for you to answer this in your own. First one is the average score of a 100-item math test was 87. Is it descriptive or inferential? Second item, we have the Department of Education predicts 20 million enrollees for the school year 2024 to 2025. Third one, we have a professor computed the sample average exam score of 200 students, and it is used to estimate the average exam score for 1,500 students taking the exam. And the other one, the last one, is a survey from 2,234 students conducted found that 55% of the respondents were not ready for the school year. Okay, so now let's identify. Number one item is actually descriptive. Why? Because it only uses the average. So just defining that the average score of this 100-item math test is 87. There's no inference, there's no conclusion made from this, there's no prediction made from this. It's just describing. Second one is that this one is inferential because the department or the DepEd were able to use data from the previous. That's why they were able to predict that there will be 20 million enrollees for this school year. So that is making inferences out of the previous data. The third example is also another type of inferential because the word there is estimate. So there are 200 samples which was used to estimate the score of the 1,500 students taking the exam. And the last one is that it is a descriptive. So why is it descriptive only? Because it's just, again, describing the data. So 55% of 2,234 students were not ready for the school year. There is no inferences being made. So again, those are examples of how we determine descriptive or inferential situations in a statistic. Now let's proceed to the variables and the types of data. So we have qualitative or quantitative. When we say qualitative, we use textual to put a name on that variable. And when we say quantitative, we put numbers. We count. There are also types of quantitative. We have discrete and we have continuous. Discrete takes the whole number, counting number. Continuous, however, takes assume infinite values between any two specific values. For example, in the case of adding decimal. A good example of discrete is the number of students I have in this class or in this course. But when I say continuous, my, for example, my weight, my height, that can take point. For example, I can say my weight is 54.5 kilograms, just for example. So it takes a decimal point, and that's a continuous variable. So the classification of variables can be summarized as follows. So we have either it is qualitative or quantitative, and under quantitative, it could be discrete or continuous. Now, in addition to classifying it as qualitative or quantitative, we can also have levels of or measurement scale to identify if that variable is nominal, ordinal, interval, and ratio. So these are the different levels of measurement. I'm just going to define it, and later we will have an example of it, each example. So when you say nominal, we are just classifying the data into the categories. So take note of the word, it doesn't overlap. one is different, is distinct from the other. We cannot say the other is higher or the other is higher because of their categories. However, when we put order to that data, we will be using ordinal level. So it can be ranked now. So there's already first, second, and third. When the order now has differences between the units, then it's already an interval level. But there is no meaning of zero. So zero doesn't take its own value in interval level. When there is also a presence of zero, then there is what we call ratio level. So ratio exists when same variable is measured in two different numbers of the population. So the same population, but there are different numbers being compared. So these are examples of nominal data, ordinal data, interval data, and ratio. So going back to the example of nominal, male doesn't is the, when you answer for male or female doesn't mean male is higher than female. So it's a nominal, it's only category. Okay? And when you say ordinal, example the grades. So if you get A, B, C, D grades, there's already an order. So A could be higher than B, and C could be lower than B, and so on and so forth. Of course, judging as well. There's a first place, second place, and so forth. And rating scale. You put poor, good, or excellent. So those are type of ordinal level. However, when there is a difference already of each measurement, because when you say poor, good, and excellent, there's an exact difference between the two, a difference between the three levels. But when we say there is a difference, now different intervals on the word interval level, then an examples of that would be the SAT score. The SAT score could differ 5% or 5 scores or 3 scores or 1 score. Compared to poor, good, or excellent, there is an equal differences among the levels. Okay? IQ, your IQ also may be different from the other, and from the other. But doesn't always mean that the difference of the two being compared is equal to the difference between the other. Temperature is a good example of interval that doesn't take zero as a or there's no like what we call this. There is no equal or there's no true value of zero, because in temperature, if you say zero, doesn't mean you don't have you cannot feel. It's actually super cold. It's a what we call this freezing point, right? So the zero value doesn't take its own value in interval level. In ratio, for example, we have height, weight, time, salary, age. This is the time when zero takes its own value. If you say zero, there's no height. Zero weight, there's no weight. Zero time, there's no time. Zero salary, you don't have salary. That's it. So those are examples of nominal, ordinal, interval, and ratio level. Now, for data collection in sampling techniques, there are 4 basic methods, but these are not limited to this. Some references would add additional, especially for non-random sampling. But here, we will just be focusing on the most systematic, most used approach in sampling method. First is we have the random sampling. So random sampling is a sample in which all members of a population have an equal chance of being selected. So when that would mean when you use this one, that could mean you are giving equal chance for the entire population to be chosen as a sample. A good example of this is a lottery or a draw lots example, in which you consider all the names, you put all the names in could be a box or could be whatever, but make sure that you make all the names so that you consider all the population. Then you get, for example, 5 samples only. So that's a random sample. There's another one. We have the systematic sample. So in this one, you have a rule. You can make a rule. For example, you have 50 students, and you're gonna get the third, for example, in each row. So you count, and then you put the rule every third member. That would be systematic, right? Every key member of the population. The other one is we call it stratified. So stratified is from the word strata. You have a population and you make a group under that population. For example, junior high school student, and your strata would be grade 7, grade 8, grade 9, and grade 10. So you pick each proportion of grade 7, grade 8, grade 9, and grade 10, depending on their population as well in each subgroup. That is stratified. You consider all the strata to get your sample or to choose your sample from. However, when we say cluster, it is dividing the population into sections and considering only one or more cluster to become your sample. And this is used for a large geographical population. For example, in Davao City, you like to survey. You can cluster them into District 1, 2, and 3. And if you say, I'm going to use cluster sample, then you would say, you can pick either cluster 1, cluster 2, or cluster 3. When you say cluster 2, then most of your sample is clusterized in this District 2. So again, this is dividing the population into cluster and only picking 1 or 2 clusters out of that population. Unlike for stratified, you consider all the stratas or all the subgroups to get a population from, right? Next is we have the frequency distribution, and graph. So there are ways of presenting data. We can have it in table or we can have it in graph. So frequency distribution organizes raw data into a table form using classes and frequencies. So an example of it would be this one. Okay, so take note, we have class limits, or we also can call it class interval. This one can also be named as class interval. And we have class boundaries. These class boundaries, where did we get this one? Actually, this value, 57.5, is just our 58 minus 0.5, and that's 57.5. So in class limit, there's what we called lower limit and upper limit. So to get these class boundaries, all you have to do is to subtract 0.5 from the lower limit and add 0.5 to the upper limit. One way to understand class boundaries is understanding that where the first interval will meet the next interval. So you can see there. Now, this is the formula that we have, and here's the example as well. Now, let's talk about how to what we call this, formulate a frequency distribution table out of this raw data. So this is an example of raw data. First step is we determine the number of classes. Now there's no exact number of classes. It depends on the type of data you have. So you can actually observe. You can make your observation. If the scores are concentrated to each other, obviously your class size will also be higher. Somehow, if they are close to each other, then your class size will be small or smaller than it is used to. So the next is after you determine the number of classes, from could be 5 to 20. More than 20 would be questionable, and below 5 would also be less reliable. So again, it depends on the data that you have. But as you can see, if we're going to make an observation from this raw data, we can say that they are almost close to each other, right? So the next one is to tally the data based on the class limits or class intervals that we will be doing later. And of course, from the tally, we make the numerical frequency and the cumulative frequency. Now, let's try to do this. First is I'm gonna identify my lowest score. So if we're going to deduct, our lowest score is 42. Our highest score is 69. So from this, you would say that highest minus lowest will be 69 minus 42. So that is 27. Sorry, 27. So if I have 27, the manageable number of classes would be 5, 6. I can have it as 7 because again, the scores are more closer to each other. So then we can say 27 divided by 7. That would be around 3.8 something. So it would be round up. Do not round up because there's a decimal already. So you consider it as 4 to the closest whole number. Okay, up, not round off. So when you round off, it would mean it will depend on the decimal point, something. So now we put our first class limit. You may start with class limit, or we call it class interval. You may start with the highest or may start with the lowest, depending on your what we call this value, or depending on your preference. But for me, I like to start in the lowest score. So I can just say 42 plus 4. That gives me 46. And then I'm going to subtract 1. Why so? Because if you count it into your fingers, 42, 43, 44, 45, those are already 4 numbers. So I'm going to stop with 45. So that's my first class interval, 42 to 45. Then so on. You'll have 46 to 49. Then you have 50 to 51. And then you'll have 52 to 55. Sorry, this is not 50 to 51. That is 50 to 53. 53. And this is 54 to 57. And this is 58 to 61. This is 62 to 65. And 62 to 69. So we adhere to have 5 classes earlier. So we're going to check 1, 2, 3, 4, 5, 6, 7. So we have 7 class interval. But we're not done yet because we still have to tally. Okay, so let's say this is our class intervals already, the class limits. So now the next part is to tally how many scores in this raw data falls under 42 to 45. So if we're going to count that, you have 1, 2. So you have 2. And so on and so forth. So you can pause the video and then you can check it in your own. So here, if we're going to count, we have 7, 46 to 49, we have 8, we have 16, we have 5, we have 4, and we have 2. And this is all 44. So again, you can one way to count would be if I'm, for example, I have used already the check. I can use the X for 46 to 49 just to make sure that it doesn't mixed with my other class limits. Okay, so these are now our frequency distribution table. Now you can also make your less than cumulative frequency here. So the less than cumulative frequency will always start with the lesser. So the less than cumulative frequency starts with the lesser class limit or the lower one. When you say greater than cumulative frequency, it starts with the highest class interval or class limits. That's it. So in this case, let's say we're going to add less than cumulative frequency. So let's start with 2, 9, 17, 33, 38, 42, and 44. Exactly the same in what we have for the total number of frequency for our different class limits or class interval. Okay, so this will now be our frequency distribution table. Now, other ways of presenting will be through the use of graph. So, of course, this is the most commonly used graph is the bar graph. So it can be presented, we can use vertical or it can be used horizontal. So the height represents, or the height or the length represents the frequency of the data. So if it is more than, and as you can see, it will be height, length, more, as you can see, it's vertical. So that's why auto has 25. That's why it's the highest one. Now, Pareto chart is another way of presenting data through graph. However, it is different from what we call this bar graph, because in bar graph there is no what we call this there is no spaces here in Pareto chart. In bar graph, you could put the data in order, but however in Pareto chart, remember it should be in highest to lowest. Now time series, so this is also what we called line graph. It tells time, of course. It tells change over a given period of time, just like this one. So as you can see, there is a change from going up until 5, continuous until after 5, after some time, the temperature is dropping down. Pie chart, this is also commonly used. Circle 1, use circle 1 for this. And histogram. Histogram displays the frequency distribution table. So if we're going to have a graph that will represent our frequency distribution table, histogram will be the best one. And we have the dot plot. Dot plot is used for data instead of the bar or the length that would represent the number of frequency, we use dot instead. So as you can see here, so one way to, so in year could be 20 or whatever year is this. It is represented by there are 3 tropical storms. So in this case, if we're gonna use, we have to get the 1971 to 2010 ranges for these years below. Okay, so that's an example of that plot. So those are the commonly used graph in statistic. Now for classroom exercises, we will be doing this in the classroom. Please take a screenshot and try to answer it before we'll meet on Tuesday or Wednesday. Thank you so much, and we will see each other again on the next recorded video.